Welcome to the Power System Protection course. We will be continuing with wide area measurement based protection. In this lecture, we will see different applications, how synchrophasor data can be used. In the last class, we discussed on to avail synchrophasor data from PMOs or relays with GPS or like other devices, data recorders and so in a substation. This time synchronized data gives powerful applications which is of relevance to the grid in grid operation for reliability and for better management. We discuss about data from PMU. This is a phasor data, voltage and current phasors in our laboratory collected from different PMUs through a PDC. This shows at different instant of time, different instances, different seconds. In between consecutive time 2 seconds also, we can have several collection of such phasor data. So, this talks about frequency, voltage, magnitude and angle, phase A, current magnitude and angle of phase A, and like that for phase B and phase C voltages and currents. So, such synchronized data at any instant of time gives a scope for numerous applications in power system, in particular even protection also. In protections applications, such synchrophasors can be applied in two aspects. We can broadly divide offline and online. Offline, it means that relay setting perspective which requires parameter of the lines, say distance relay, impedance of the line and so, which can be obtained from the synchrophasor data also. So, like that we can have offline application and also we can have real time applications on protection decision perspective. But the important difference here is that these wide area measurement system which is associated with PMU data are having latency, and this latency has different aspects and components. We have discussed in last class that the PDC level, phasor data concentrator level, the at the PMU level itself, also with the communication infrastructure and so. So, the total latency of the system from data to the while it is being processed for particular application. So, this latency is compatible to a particular protection or not, that is that has to be first checked. And as you see here, with the associated latency, such protection from wide area measurements are mostly for the backup arrangement. So, we have individual protection through the relays, as we have already discussed in several lectures earlier, line protection with distance relay, line protection with differential relay and so on. But now, what we are discussing is on the how the synchrophasor data can be applied, which has latency issues. So, this is an independent platform which can collate, integrate data and then make a decision, and that decision may not be that fast as compared to the primary protection and so. So, this can supplement the protection decision in general. Now, if one to one two PMUs are communicating or PMUs in a substation, we can have very low latency, few milliseconds, but if the PMUs, several PMUs are being integrated in an area or at central level, it can be associated in terms of larger latency, hundreds of milliseconds to as high as 1 second also. So, this big difference between the conventional protection scheme and the latency associated has to be seen in the perspective of different applications. Let us come to different applications. We will go one by one. First one is transmission line parameter estimation using synchrophasor data, synchronized data from the PMU. Note that these we have already addressed that the synchronized data or the phasor measurement unit data which we avail can be availed from the relays with GPS facility. So, this is a transmission system, sending end and receiving end. We have currents and voltage measurements through this PMU at sending end, another PMU at the receiving end, and then they have dedicated communication system for any other applications. Then how we can avail the data for parameter estimation of this line, we will try to see it. So, let us model the corresponding transmission line in terms of the pi model. Here we see that this is the Z 1 r plus j x, the series part, and the shunt part with y n by 2 and y n by 2. So, like we talk about R and L and the corresponding capacitor and the conductance. So, our measurements here from the sending end side is V s with angle delta s and I s with delta theta s, and V r with delta r and I r with theta r at any instant of time for any loading condition or so. So, then we can express the corresponding V 1 s and I 1 s in terms of the sending end currents and voltage. We can express in terms of receiving end currents and voltage. So, that we know from this you can say that model. So, then with this you can say that two expressions we can get the two unknowns here Z 1 and Y 1 as you see here from the known values of V 1 and the V s and the I s. So, this we talk about a Poitou sequence voltage and currents and associated Poitou sequence impedance for this purpose. So, on that perspective this model belongs to the Poitou sequence equivalent model. So, associated Poitou sequence voltage and currents are being dealt with and we get these relations. Now, see this how this corresponding parameter estimation with the pi model we can extend it to the other model also, including long line model, ABCD parameters and so. Let us see here how this parameter estimation can be from the phasor measurement data can be used. So, we have this 2 bus system and the line, and then this 100 kilometer 400 kV 50 hertz line at a particular loading condition. PMU measurements are available as in this table, and then we have to estimate the parameters using the expressions as we derived in the last slide. So, true values of this Z 1 and the Y 1 Poitou sequence impedance and the series path impedance and the admittance are given as like this. These values are used in the simulation, and then we for a loading condition collected the PMU data from the PMUs and the PS card, and then using this data we find the Z 1 and the corresponding Y 1 as expressed in the last slide. So, substituting these values from the synchronized data, we get the corresponding Z 1 equals to 2 plus J 28.58 as compared to 2 plus J 28.67, and the Y 1 equals to 183.11 into 10 to the power minus 6 Siemens as compared to 183.78 10 to the power minus 6 Siemens. So, this shows clearly that the estimated parameters using the PMU data or synchronized data are pretty accurate. So, it means that such data, lane data can be used for relay applications or any other applications for the system. Now, furthermore, we are going to the second applications, how synchronized data can be in real time can be used for substations measurements for the accurate data, accurate information for the at the substation level. two aspects, one is the voltage, the other the current. So, first we will see that how voltage measurements can be obtained in a better way at a substation. We know at a bus, at a substation, there are several measurements including that for the voltage also. So, these relays, they have the corresponding voltage measurements through the PT or CVT connection, and they compute the phasors, and if these relays are having GPS, they can provide synchrophasor also. So, assuming these are corresponding synchrophasor platform or equivalent to that PMU. So, we say that the relays, let us say here 5 relays are there, these relays provide us also the synchrophasor data, and now consider this for the voltage measurements. So, at this one, because they are measuring the same voltage, so therefore, all the voltages should be same, but because of this PT and the associated computational process and the performance of the relay or the PMU, the accuracy will be of different in nature, and therefore, you can say that we will have the, even though you are measuring the same voltage, we will be having different measurement as shown by these relays or PMUs. Let us say here the each measurement by these devices can be expressed in terms of V I equals to E I plus epsilon I, and we have 5 measurements here. V is the measure voltage, what is being displayed or provided by this device, and E is the true voltage, the correct voltage. So, what we will do that we will calculate this delta V I, that equals to V I minus V j, where I and j are the corresponding measuring devices. So, we will find the corresponding deviation as compared to between all the devices for all the buses, measurements and so. So, we will see that this delta V I should be greater than a threshold, then we flag it, note it, and if that is considered is there, then you do not use it further. So, note that we notice from there that there is some erroneous measurement in the system and so. So, you have to discard that measurement, and then you can say that you can best estimate of the measurements by, I can say that, getting the average of these corresponding measurements after discarding the erroneous measurement. Such average measurement becomes more accurate value for the further application in the substation or at the any remote end. So, therefore, this processing leads towards bad data rejection at a so simple level of computation, and also an accurate value of voltage phasors it provides at the substation level, which can be dispatched to the any control center for further application. We will see an example on voltage measurements. At 11 kV generating station, we have 5 bus measurements like that what we see. So, these 5 meters devices, relays, PMUs, they provide V 1, V 2, V 3, V 4, V 5 at one instant of time, one loading condition like this 10.54 with angle 0.21 degree and so. And these 5 measurements if you see, clearly there is a large difference between V 5 and rest of the measurements. So, as you see, there is a chance that there may be error with the 5th measurement. So, what do you do that, as already mentioned in the earlier slide, we find the voltage difference. So, we calculate like this V 1 minus V 2, V 1 minus V 3, V 2 minus V 3, V 1 minus V 4, V 1 minus V 5, V 2 minus V 3, V 2, this is second row, then V 3 minus V 4, V 3 minus V 5 and then V 4 minus V 5. So, we have 1, 2, 3, 4 columns for these differences. So, now what you notice that out of this we check here, you can say that V 1 minus V 5, all these V 2 minus V 5, V 3 minus V 5, V 4 minus V 5, all these difference values are significant as compared to the other differences. So, this gives us a score to check that whether this V 1 minus V 5 here V 5 is common in all the differences. So, we doubt about the V 5, and if this V 5 you can say that this V 5 is flagged because the difference is significantly high. Let us in this case we have considered a 1 volt threshold, and this is crossing 1 volt threshold in all the differences. So, we flag V 5 and discard this measurement. So, therefore, the corrected value after discarding V 5, V 1 plus V 2 plus V 3 plus V 4 upon 4, and that gives us 10.74 with angle 0.2 degree. So, this value should be used at the substation level or should be dispatched to the other centers. So, this gives us a refinement perspective for the substation voltage and gives a scope to discard bad voltage measurement. Thereby, we can suspect the associated PT or the device itself, and then we can have the correction for that. Similarly, in a substation we can have these corresponding current measurements, and in current measurements we can apply Kirchhoff's current law. Then this current law can be used for checking whether measurements are correct or not. So, some of the current measurements at a bus, all the measurements with all measurements incoming to this bus, if this summation is close to, ideally it should be 0, is less than a threshold, then we declare that the measurements are okay, otherwise we suspect. If above condition is valid, then the current measurements are refined or goes to the further refinement, or we can do process something. Otherwise, at least one of the measurement is assumed to be bad. So, refinement is not possible, unlike that in voltage what you see. So, we define error here, the epsilon equals to sum of all currents plus I 1 minus A 1 for this I 1 current. This is that I 1 cap is the estimated value and A 1 is the corresponding measurement. So, I 1 minus A 1 plus I 2 minus A 2 plus I 3 minus A 3. So, that gives us the corresponding error part for individual branch, and then we have summation of this currents also. Summation of this current, as you see here, should be KCL said that it should be close to 0. So, with that error, if we write that corresponding error equation in matrix form, what we have seen there, this becomes equals to 1 1 1, 1 0 0, 0 1 0, 0 0 1, I 1, I 2, I 3 minus 0, A 1, A 2, A 3 equals to 0. So, using the pseudo inverse to get the corresponding estimated value, which will be representing the correct value of these measurements. So, therefore, that I 1, I 2, I 3 can be obtained from the pseudo inverse of this matrix, and then we have A 1, A 2, A 3. So, that leads to situation we can say that from the above equation, for this equation you can simply mention also that individual current estimated to be estimated, that equals to the corresponding measure current minus 1 upon n plus 1 summation of A j. So, this is from straightforward from these relations. So, the small n corresponds to the all currents directed inward, agree, then only KCL becomes valid perspective. Now, we will see example for this case 3 measurement system. So, let us say A 1, A 2, A 3 are the measurements, and these are in the first set. So, this is case 1, and we see the corresponding measurements in this process. The KCL sum becomes equals to pretty small value. So, we say that no refinement is required, e to the power minus 13. So, we do not require any refinement and so. Now, what we see here in the second set, that these are modified of these measurements, intentional errors are being put into this data plus some error, and we see now the corresponding KCL we apply. So, then this becomes equals to 3.39, 2.8, and then we have a threshold as already mentioned in the earlier slide, the KCL summation becomes less than 5 ampere. So, this is acceptable. So, we can go for this refinement. So, from this set 2 which are having little erroneous data as compared to the set 1 for the same condition, then we see that the corresponding currents after the refinement, you can say that using that relation of matrix either pseudo inverse or the simple relation, then the refined currents are becomes this, and we found that the KCL summation becomes equals to 0.84, 2.8 as compared to 3.39 in the actual measurement perspective. So, therefore, we see that the refinement reduces the error in that perspective. We have another case of current measurements from the same A1, A2, A3, 3 measurements. These are better measurements, and now we added, you can say that errors into this, and there is significant difference between the A1 and the first measurement. Here you can say that 126 here. So, this shows that if you go for the KCL, this becomes significantly high 15.73 degree. So, this crosses the corresponding 5 ampere threshold. So, it means that there is a bad data here, and that bad data in that stage in that case we cannot have a refinement perspective, because we have to apply KCL. So, this shows two cases. In one case we have a bad data, and in one case refinement is possible. Now, in furthering our application perspective, line differentiated protection using synchronized data, we have seen this application in line differential perspective, and already we have covered in earlier lectures. So, continuing that, if you have PMU data either directly or in a wide area measurement system perspective, then you can use this PMU data for this line differential protection perspective. So, this can act as a backup, or also normal with GPS technology and all these things, we can have synchronized data and you can use as a primary protection also. So, this if you have indirect way of collecting this data from any other applications the PMUs are available. So, this can act as a backup also. So, synchronized measurements gives us that I 1 minus I 2, otherwise you cannot do, as already pointed out the concept of synchrophasor. So, that only thing is that if the reporting rate and the corresponding associated latency are compatible to this particular protection requirement, then this can be directly applied. The advantage of such a differential protection is that if the line is having capacitor, having FETs devices or multi-terminal line, then we can explore such facility for accurate protection schemes. And so, multiple lines may be emanating from at different points. So, in that case the best solution will be the differential protection, and if you go for synchronized data, then it becomes easier and more accurate. Fault location we have seen in travelling wave perspective. So, there also we mention about if we have synchronized data at both the ends from PMU applications, fault location is offline business, there is no issue of speed and so. So, in this case if we have a fault at x, so then you can write down from this side single phase, simply a basic equation if you write, and then you can extend to 3 phase concept also. So, the Vm can be equals to Vf, the fault voltage here, plus this drop. So, this is x ZL Im, and then this side also you can have Vn equals to Vf plus this current and this drop. So, 1 minus x ZL In. So, this idea. So, what you say here that if you can do Vm minus Vn, if both are synchronous data, then you can do Vm minus Vn, otherwise you cannot. So, then Vm minus Vn, it means that the Vf, the fault voltage cancels out. So, in that case using Vm minus Vn, you can get this x to become, so only unknown becomes x from this Vm and Im management, and then Vm, Vn and Im and In, and then this x can be expressed in this fashion using the voltage and current measurements and the line parameters of the if it is positive sequence and like that, or negative sequence. So, this is for the 2 bus line 100 kilometer line, the line impedances are like this, and we say that RF V1 the fault resistance variations of 0 ohm, 10 ohm and 100 ohm for 3 different fault situations, phase A to ground fault, and then we have got the V1, V2, I1, I2 of both these sides measurements, and then we apply this, you can say that from one end you can say that from this end if you do, then the corresponding fault was having at 25 kilometer from this side. So, we got the per unit distance to be 0.25 for 0 fault resistance, but with increase in fault resistance the impedance based approach gives us erroneous fault distance, but 2 end synchronous data the formula we used in the last slide. Using that you can say that in all the cases we are getting 0.25, because the VF fault voltage does not influence the corresponding accuracy. So, this is the strength of synchronous data being used for fault location application also. Now, next we will go for another applications in real time perspective, how the corresponding PMU data can supplement zone 3 protection for better decision. In this perspective, we say faulted line identification. So, what you see that any line having a faulted in this system 9 bus system here. So, we see if that can be identified from these different measurements of the from the PMUs, then we can use that for you can say that backup protection for that perspective. Let us consider a situation here how that can be extended. Let us see the issue. Now, see failure of relay at bus 5 as backup protection for relay at bus 7. So, from this one this part is taken care. So, you see here failure at bus 5 this bus 7. So, the relay you can say that bus 7 fails to protect for this fault, let us say 3 phase fault that is towards the end in zone 2. If this breaker does not operate, this breaker must operate. So, that means that for this it will be a zone 3 fault. Now, what happens to the situation you see here. So, Z set for this at bus 5 for its zone 3 equals to 1.2 times impedance of this line plus the impedance of this line longer line. So, that becomes equals to let us for this case is 248.46. But the Z seen at a given instant of time because of the infeed from this side happens to be 316.7 ohm. This voltage upon this current that gives us 316.7 ohm because of the infeed from bus 2. So, that leads to a situation of that this because its setting is 248 only and now it is apparent impedance is 316. So, this relay at zone 3 will not pick up. So, the fault will continue because breaker at this point is not able to clear the fault. So, that means that the Z seen that. So, therefore, that will continue. So, the inability of the zone 3 at bus 5 leads to dangerous situation. So, with PMU data we can identify the faulted line and then this if that bus at bus 5 breaker can be open from an independent protection arrangement that can supplement the available protection schemes, then it will be better. Now, the question is how that can be implemented. So, for that perspective let us say in this system 9 bus system we have few PMUs at bus 7, bus 9 and bus 4. Now, how this data can be used for faulted line identification and then how we can supplement the zone 3 protections, that we like to put an example. Now, what do you do that? We see this fault in line 8 9 and in that case the corresponding voltage everywhere dips and as you know that the voltage dips to a greater extent at the adjacent buses. So, bus 8 and 9 should be affected. So, you see here you can say that the corresponding E8 is this one. So, that goes to significantly low and this side is generator. So, that region is little bit higher. So, that what I would like to say that if you see this magnitude and dip in these voltages from 1 PO is clearly observed and further the corresponding electrically further the corresponding bus the corresponding dip will be smaller and smaller. So, what do you do that short the voltage to identify the faulted line, bus with the lowest voltage being selected and line with highest phases, which line whatever lines are connected to the that lowest voltage bus the phase angle difference between voltage and the current connected to the bus indicates the faulted line, because the phase angle will be indicative of direction in that perspective. This phase angle will be indicative of direction. So, what we like to say that the PMU data here can be useful for decision process which add value to the protection scheme. Now, let us see an example here what is being done. So, we have 3 PMUs and a fault happens to be there and between bus 7 and 8. So, at that time we collected data in the simulation process. So, at bus 4, bus 7 and bus 9, these are the PMU data, positive sequence data, 3 phase fault happens to be there. So, E4, I4 6, I4 5, the corresponding line. At bus 4 we have 2 lines 4 5 and 4 6. So, these are the currents, associated currents. At bus 7 we have 2 lines, this line and this line, the currents are there, and bus 9 we have 2 lines 9 8 and 9 6. So, all currents associated that PMUs are also available, including the voltage. So, 3 voltages 291, 115 and 210. So, the minimum one is 115. So, we bring out this corresponding bus 7 as the choice of the lowest voltage bus. So, that is what bus 7 selected in this case. So, after this bus 7 we say consider at bus 7 the corresponding currents are I 7 8 and I 7 9, and then we check we consider with this voltage bus 7 voltage which current is having larger angle. So, we say consider the highest phase angle difference between E 7 and I 7 5 which happens to be there. So, therefore, line 7 8 this is I 7 8. So, this you consider angle tells about that line 7 8 is the faulted line, line 7 8 the faulted line. Another case we see here, fault is created between 9 and 6 and the measurements are this. So, in this set positive sequence voltages and current, we say the minimum voltage comes out to 104. So, bus 9 is selected, 2 lines are there 9 8 and 9 6. The angle between this voltage and this current, that happens to be significantly high. So, the corresponding 9 6 line is selected. So, 9 6 line is selected. So, that is the correct value. So, in both the examples we see that from the PMU data, if available, we can find the faulted line correctly, and this faulted line can be useful for further information processing. How? Now, what you see that this is that 9 bus systems and we have PMU, we collect at a control center to this PMU, and this control center can process the corresponding PMU data, align them in terms of the time alignment, and then it can be used. So, we have these 3 PMUs and then we calculate the corresponding faulted line, identify the faulted line perspective using this at the PDC and the controller level, this level. And once you calculate that the fault in zone 3 or not, so we calculate the relay for the different relays at the central edge level. We calculate that is the corresponding fault is in any zone 3 of any relay here. Yes, if it is yes, then the corresponding relay should remain active, otherwise you can say it should be blocked. So, a command can be issued from here also through the relays at different points to activate the corresponding breaker in the stipulated time without waiting for that. So, what is the advantage of this, that such a platform can give us in terms of hundreds of milliseconds, and then therefore, we may not have to wait for 500 milliseconds to 1 second which the conventional zone 3 operates. So, that will speed up the process of decision, because it will be able to know that it is a decision of the zone 3, zone 1 is not operating. So, therefore, you can say that or zone 2 is not operating, there is a failure. So, it can go for the protection decision at a faster rate. So, thus we see that PMU data can be used for as a backup arrangement, as a supplementary arrangement to the zone 3 protection perspective, which seems to be compatible from latency issue also. Islanding detection, for the larger system we talk about out of step protection. If the rest of grid side is having problem, then to retain this local area we can say that an islanding in the island situation. In that case, the local area should manage the corresponding load and generation, or it should shut down all its generations to bring it to a standstill. In a distributed generation system, we require also islanding detection, that we do generally from the frequency information or voltage information perspective, but we can also use the corresponding PMU data or synchronized data, and like this, in this case this is a power system, and then we have this is connected to consider to this connected to this local power system is connected to the corresponding PV plant, and so any renewable resources or DG, and this side you can say to the ball power plant. If this corresponding ball power plant connections is disconnected, then this local system either it may not be able to manage with this corresponding PV plant or renewable generation. So, in that case an islanding detections, the PV plant should be disconnected, because otherwise it will lead to issue with the safety of the personnel, equipment damage in the locally, and also the power quality issue. So, for that reason you can say that the islanding detection becomes an essential one, and in that case the local islanding detection schemes can be useful, and if that fails also, if the PMU data are available, it can supplement that either at high voltage side or in the distribution system also. For that, the angle between the two voltages, this side and that side, that angle is indicative in case of this islanded systems. If this breaker is open, the angle drifts independently between these two, there is no synchronism between them, and therefore, it will drift, you can say that, to any in the forward or backward directions. So, that angle is indicative of the corresponding situation. Normal situation, when grid is connected, this delta angle becomes smaller, and it will be consistently having a closure value to the steady state value. So, therefore, this corresponding angle is indicative of in terms of the islanding situation, its derivative or double derivative can be faithfully used for such detection. System integrated protection scheme is a concept which is already there in the system. Most of these system integrated protection schemes use this carrier data also. Note that system integrated protection scheme is different from the conventional protection. Conventional protection address individual element like differential protection for transformer, line protection with distance relay or differential arrangement for individual line, distribution system, and so generator protections. These are individual protection we talk about, but system integrated protection schemes are installed to protect the integrity of the power system or strategic portions thereof, whereas conventional protection is for element wise, element specific protection also. This is to retain the system intact, its integrity, particularly from possibility like large scale disturbance, blackout, and so. This SIPs encompasses special protection scheme, remedial schemes, any integrated scheme, and it also includes under frequency, under voltage, and out of step functions to retain the integrity or the integrity of the system. These schemes provide reasonable countermeasures to slow and to stop cascading effects for evading possible large scale disturbances. Synchronized data provide a good platform for such applications. So, we will find many applications today in different grids on that perspective. The SCADA systems which is catering these SIPs can be supplemented with wide area measurement systems, because that gives us a better scope for such applications. Let us see an example how in Mexico grid SIPs using synchrophasor data is being implemented. So, this is a part of the Mexico things. Chicosen, Angostura, this 400 kV line, there are parallel lines, double circuit line, and there are number of connections for the 100 kV line, 115 kV network. So, what happens that these 900 megawatt generations pushes power, you can say that, to the national grid, other portion of the system to double circuit line, and also there is a connection of 115 kV line also. Now, what happens in case of any of the line trips in this 400 kV line? So, the rest of the power will be dispatched through the 115 kV line. In that process, the 150 kV line gets stressed, and there is a possibility of this 150 kV line at different portions can be overloaded, and overloading operations will go, and then that leads to different several outages of this line, and may cascade events may go, and that leads to more stress in the system from this generation units to the national grid level. When both the lines are out, it is more severe in nature, and then you can say that there is a chance that this region can be out from the national system level case. In that case, this to avoid this situation, particularly the contingency of double circuit line outage at 400 kV level and so, the requirement becomes the utility must set this generator to reduce the generation or to withdraw all the generators at this location. So, what is being done? We see here that we have a PMO placed at this end, and we have PMO at this end through available relays and so with GPS facility. Now, this PMO sends data informations to this one in real time through communication system, and the corresponding voltage data here and voltage data here, they align, and then from the alignment the processor here does see that what is the angle deviation between this side and this side. Note, now when the corresponding angle in general is in a limit, when 400 kV both lines are there, one line is out, the angle between this side and that side goes to be higher value, and when both lines are out, the angle becomes further higher. So, that is being noticed. So, in this automatic generation shading scheme, generator shading scheme, so that hydro plant giving 900 megawatt or so. So, a method to detect loss of transmission capacity is by this, you can say that this angle measurement between these two sessions. So, that is being used. So, what is being done here, that the double line outage produces 14 degree angle between these two sides, and one line outage provides around 7 degrees of angle difference between both ends. So, a threshold of 10 degree is being selected, and then you can say that between these two phasors. So, angle between these two voltage phasors, local one at the generating station side and the remote one. So, these two angle difference gives us delta, and if the delta is greater than 10 degree, then it is a tripping of selected generator is to be accomplished. So, this gives that once the generator the generating station reduces or the generators are out, then the stability of the system can be retained, and the cascading trippings and so can be avoided in this perspective. So, this gives a systematic protection schemes using phasor measurement units at remotely placed PMOs. So, in overall we say that synchronous data from PMOs from relays with GPS facility can be used for different applications. We have real time applications as well as offline applications which of relevance to the protections perspective, that we see like SIPs for online applications, differential protection and fault identification for zone 3 application perspective, and also for offline perspective for parameter estimation and so. But in real time applications, latency is the challenge, the late arrival of data. If that is compatible, the corresponding synchronized data through wide area measurement systems can be a good addition for system level protection, including element level protections as a backup or supplementary. Emerging technology this field is, and therefore, newer and newer applications are coming on in different grids. This also such technology is not only limited to this is also going on for the control applications of the power system and also for monitoring applications. So, this is the last lecture we have for the power system protection course. Our focus was on numerical link principles, algorithms which are available today and are being used in the different applications in the grids. Many more relays are available, many different protection schemes are available like generator protection and so. This is beyond the scope of this course. This course dealt with the basic in nature. If anyone desires to be more details on this, lot of resources are available. We hope you enjoyed the course. Any remarks, comments, so always welcome. There is definitely some errors will be there. If you can point it out and communicate to us, it will benefit all of us. Thank you. Best wishes.